Good afternoon, everyone. So first, I talk about several things regarding the quiz. The quiz you can give me next week, okay? And do your best next week. If you can give me next week by Friday, and I will be very happy. My bottom line is that you give me a high quality, the model, high quality table. Everything is high quality. I don't want you guys to finish everything in a hurry and just does not make any sense. That is one thing. Second thing, I do not have the problem statement. Can I borrow problem statement? Yes. Yeah. Okay. Which one? Okay. For table 2 and table 3, the first of all, table 4, we will not use just cut off the table 4, okay? The table 4 is between FEM, that is the displacement control. And because answers, maybe you are not very familiar with answers, so we will not do the displacement control. That means just delete the table 4, okay? So table 3, yeah, table 3, you compare, so when I talk about the model, I just talk about two versions of the geometry. So if you use this model closely, okay, and so you can compare your numerical results with the analytical results. However, if you use another version of the model, I told you guys the whole is A for another version, and then you cannot do the comparison, okay? And because that analytical model is specifically for this geometry. So as I said, either version will be okay as long as you are consistent, your results are consistent. You understand? So if you are using another model, another geometry, and you can just write for the table 2, you can just write what is your value, and then write this analytical value. Analytical value, you just for the analytical model results, you can just use this one and to calculate the analytical model for this one, and then you don't need to compare. Just tell me, and you are using that geometry. That is totally fine. Okay. However, if you are closely using this geometry for your answers model, and you can do the comparison and tell me something, make some comments.
This geometry means both parts includes that's like two parts.
Yeah. Okay.
Yeah, okay.
So, because last time I told you something different. Okay. Any questions regarding the quiz? Any questions? It will be due next Friday. I want next Friday will be the last time we have I can extend. Will that be okay? Next Friday, not this Friday. This Friday is the fall break. Next Friday, I think is November 1st, right? You finish everything and give me, and because we are going to have other homework assignments. Right? So questions regarding the quiz? Follows.
So you want 3 of these Excel graphs, right?
Yeah, give me Excel.
3 of these?
Yeah, it will say if it says Excel
Yeah.
and show me the Excel sheet. Okay? It's just a screenshot. Screenshot will be okay. Another thing is for this is the midterm. So midterm, I think there's a lot of students they do things wrong, right? So for this kind of crack, so this is the edge crack. For the edge crack, so this is K. The Ki equals 1.12, and this is a sigma square root on pi a. So while a lot of students you just ignore this is the constant, right? So this is for edge crack, and suppose we have this is a sigma, is a remote stress sigma. And so for if it is a central crack, if this guy is a central, the through hole crack. So for this is a 2A. If we have this kind of central crack, okay, so this is infinite, okay, so this is infinite. So for this one, the Ki equals sigma and square root of pi A. Right? You have sense? Okay, so this is the midterm. The midterm for the three kind of calculation problems, the solutions are posted. And as I said, and you can give me a redo, and the redo will be due next Friday also. Right? This is optional. Now the redo, if you give me the redo, and I will check to see if you have fixed all the problems or not. If yes, you will get 50% back, based on the points that you have lost. What? Make sense? This is optional. This is not mandatory. Also, on the midterm and midterm redo, and we only have one value. You have sense? I will not carry two, both of them, for the final. Easy. Are you confused? Okay, that means suppose, okay, so suppose we have 100 points. I told you guys already. And for some reason you get 80 points for the first try, and then you do the redo, and you get 20 points. 20 points multiplied by 50%, and so this is the 10 points. So finally, your result, your score for this midterm will be 90%, 90 points. So 90 points will be the only value for your midterm. Alright? I just want to clarify everything, because based on my prior experience, some students ask, and they are afraid of that, and we have original score and also this is a reduced score. No, only one. Without further ado, I'm going to continue our talk about this is the fracture mechanics for this is the metals, and we know that for the metals we have four types of fracture mechanism, and one is called the microvoid coalescence, and this is for ductile material. And suppose we have microvoids as this load is increasing, so these microvoids will be coalesced with the neighboring microvoids. So these microwaves come together and they will become a crack. So this is the first one. And second one is cleavage. Cleavage is usually happens for this brittle material, and also cleavage, it is transgranular break. That means the crack will go through these grains. So this is the transgranular. The third mode is fracture mechanism is intergranular fracture. As the name suggests, intergranular fracture means that the crack propagates along the boundary of these grains. So because usually the boundary grains and the bond is the weakest one. Lastly is the fatigue fracture. So this is totally four types of fracture mechanisms. And yesterday we talked about the ductile fracture, and we have talked about several models. The continuum model and one dislocation model. And today we talk about this void growth and coalescence. So this is how to model this void growth and coalescence. So if you have done this is mechanical engineering lab, and who have done the mechanical engineering lab? Raise your hand now. Mechanical engineering lab. So you have to do the tensile test, right? So do the tensile one. When we do the tensile test, and we usually have three different materials. One is aluminum alloy, one is steel, and one is this cast iron, right? The cast iron is a brittle material, and aluminum alloy and steel, and these two guys, they are the ductile material. And we know that, and how the fracture surface of the ductile material is different from that of the brittle material. Can somebody tell me how they are different? Bobby?
Brittle is gonna be like a clean cut, but ductile is gonna neck a little more,
Yeah,
like when it stretches.
yeah, okay, great, thank you. So this is the brittle material when they break, it will tensile under tensile loading conditions. If the brittle material breaks, so they will have two very flat surfaces, very flat. Why? Because there is no plastic deformation, right? It's just a crack. And for this the ductile material, and we usually have the cup and the cone, and this is a fracture surface. So suppose at the very beginning, so this is connected together. If we have a loading, so here is a cup, and here will be the cone. So this is look like a cup and a cone with fracture. So first we talk about this model, right? So this is the shear model. This is shear cup and cone, leather shear, and just like this is lower part, and upper part is this. So this is the fracture of ductile fracture. So here is a shear, and usually it is a 45 degree, and the same thing on 45 degree here is called a shear. Our fracture mechanics, this is our job is how to predict and how to predict this crack propagation. And so first, and the Rice and the Tracy, and these two mechanics guys, and they propose a model. Okay, so suppose we have a 3D. This is a specimen, and we have a microvoid here, and the microvoid. And this case, the radius is R0, R0, and in 3 directions, and we have a sigma 1 and epsilon 1, the corresponding epsilon 1, also sigma 2 and epsilon 2, along with epsilon sigma 3 and epsilon 3. So how can we predict the growth of this R0? So this case model considers a single void, and states that the void growth in all cases and could be approximated by the following semi-empirical relationship. And empirical, you know empirical, right guys? So the semi because there's some analytical things here. Some empirical relationship. So this is R0 is the original radius of the void. The R bar is after you apply loading conditions. And so this guy grows, okay? Why do we have R bar here? R bar because this is a void at the very beginning, and we just think this void has the uniform, have the same radius, same geometry in all directions. However, and this is the 3 dimensional loading conditions, and sigma 1, sigma 2, sigma 3, and so this void will become bigger. Okay, this is how bigger in 3 directions, and they might be different, right? You guys agree? So that's the reason. So the R bar is average of the new 3 radius, so 3 radii in 3 directions. So we use this R bar. So logarithmic R bar over R0, so can be approximated using this equation. So this is a factor. So this integration sign exponent, and you can see sigma m. And can someone tell me what is the sigma m is? M means mean, right? M is mean stress. Mean stress equals the average of the 3 normal stresses. And sigma ys is the yield strength. That is a material parameter. And the epsilon equal EQ is the equivalent strain. you can do the integration. So based on this integration, and you can predict the R bar. R bar means, as I said, R bar is the average radius in 3 directions of your applied load. You can see, we can write this one, okay? dr d epsilon equals this is factor R0 exponent this one. This is the same thing. So epsilon EQ is equivalent this plastic string, equivalent plastic string. And R0 is the radius of the initial spherical void. At the very beginning, and we assume this void has the same radii in 3 directions. And R1 is this R1, R2, and R3, and can be written and using these equations, these 3 equations. And especially this is A is using this one, and B is using this, and what is the D and G, okay? So okay, epsilon 1 here, and the epsilon 1 is the total strain integrated from the undeformed configuration to the correct state. So this is epsilon 1. And also D and G, and they are constants that dependent on the stress state, and this is a strain and also strain hardening. So this here is this model. The void, you can see the void is subject to remote normal stress, sigma 1, sigma 2, sigma 3, and remote normal strain rate, epsilon 1, epsilon 2, and epsilon 3. This is the dot. If you have a dot on the letter, that means that is the strain rate, okay? And how fast you apply the strain. So that makes sense also. And we also know that we just assume this material is incompressible, okay? So this is very, very important assumption. If you assume this material is compressible, that's another story. So we need to use another set of equations. But for simplicity, we just assume the material volume does not change, no matter how you just deform it. Right? So this is for simplicity. So because of the incompressibility and the sum of these 3 and the strain rates, and they are equal to 0. So you can see epsilon 2 and is related to epsilon 1, and epsilon 3 is also related to epsilon 1 dot. And what is the phi, guys? This is the phi, okay? And this is on how we calculate this phi. You understand, guys? So our goal is that there is a theory, and we can use this theory to predict how the crack propagates. So there are a lot of theories, and we are going to talk about the typical theories that are the commonly used theories. So it is any question regarding these equations, guys? I will not say this equation is correct. I will not say this equation is wrong. Okay, but so this equation was proposed by these 2 genii and in the early stage of fractional mechanics. Yeah, definitely both of them are very, very smart, the people. Okay, how close they are when we use them now, that's not another story. You understand, guys? Because the material changes. You guys agree? The material we are using now is totally different from materials they used in 1940s. Do you agree? I think you agree, right? And for example, the steel, even though the steel is very, very simple one, the aluminum material commonly used. But now there are a lot of other alloying elements. They are added to the system, to the steel. So all these alloying elements, and they will play a significant roles and in the fracture behavior of this material. You understand? That's the reason I will not comment whether it's correct or no, but at least they are correct many years ago. As I said, as the time goes, a lot of things are changing, especially for the material, right? So let me ask you guys, how can I judge whether this model is correct or not? Bobby,
Experimental.
Yeah, experimental. right? So whenever you have a model, in order to verify your model, you must do experiments and to verify the model, to compare your experimental results with your the predicted results using the model. You guys agree? And then to do the experiments, you need to use the material, right? As I said, the material they used many years ago, they were totally different from material we are using. You have sense? Now it's very hard for us to use the current materials to validate their model. If we do it this way, and this verification is not fair, it's not fair enough. But as I said, at least their models have been verified many years ago using the materials that they used at that time. Right? Okay, I just want to let you know, guys. So, so it is noted that this model is based upon a single void and it does not take account of interactions between voids. If we have multiple voids and how this model goes, nor does it predict ultimate failure if there are multiple these voids here. A separate failure criteria must be applied to characterize microvoid coalescence. For example, one might assume that fracture occurs when nominal void radius reaches a critical value. So then we talk about another model, and it's called Gerson, and this is the Tavega model. Okay, so and also you can see. So this is a model. Model is a mathematical equation, and so Sij and Sij. Okay, so here. And the Sij, you can see, and Sij is named divitorial stress. And what is the divitorial stress, guys? And sigma ij minus sigma m delta ij. The sigma ij, and this is a sigma ij, and so this guy, we have 3 by 3, and we have sigma 1 1, and sigma 2 2, and sigma 3 3. And sigma 1 2, sigma 1 3, and sigma 2 3, and here is sigma 2 1, and sigma 3 1, and sigma 2 3 2. So here is my sigma, right? My original sigma. And what is the sigma m? And sigma m is a mean stress, and sigma m is a mean stress. So this guy is defined as 1/3 and sigma 1 1 plus sigma and 2 2 and plus sigma 3 3. So this is a 3 normal stress, right? We know that, right? So this is my original stress tensor, the tensor. So this is my mean stress. Mean stress is a scalar, and this guy is a scalar. So divitorial stress Sij equals let's use the square friendly. So sigma ij minus sigma m delta ij. What does that mean? Sigma m delta ij is this. Right? What is delta ij? Delta ij means that so this guy equals 1 if I equals j. And so this guy equals 0 if I is not equal to j. Okay? As a result, this guy equals what? This guy equals sigma m, 0 0 0 0 0 0. Got sense? As a result, this Sij, so this is divitoric, excuse me, this is divitoric, the stress tensor, and how the divitoric stress tensor is different from the original stress tensor. That only the difference is that the three diagonal elements, the three diagonal entries, okay? So you need to use original one minus sigma m. Have sense? So that means this is sigma ij equals sigma 1 minus sigma m, sigma 2 minus sigma m, and sigma 3 minus sigma m. And then we have sigma 1 2 and sigma 1 3 and sigma 2 1 and sigma 2 3 and sigma 3 1 and sigma 3 2. Okay, so this is Sij. And we know that, so sigma ij equals sigma and ji. So this means this means that this guy is symmetric, okay? And that means sigma 1 2 equals sigma 2 1. So I want you guys to know that, because some students have never learned this elasticity, have never taken the CE class with me. So, and how it works, this equation. So if this equation is satisfied, that means, so the crack tends to propagate. Right? What this equation says, you can see this Sij, this Sij, I appears twice, but because this is I, this is another I appears twice, I is a dummy, right? J is also a dummy. As I told you guys, the dummy means summation, right? So Sij multiplied by Sij, that is a summation of all, and this is these are divitoric stress components. So plus F is current void fraction. You know the void fraction, right? So we have a matrix and we have certain number of voids, right? What is the volume of the voids over the matrix? That is called void fraction. So this is cos h, and cos h is defined as it is a hyperbolic cosine. It's EZ plus EZ divided by 2. So this is hyperbolic cosine. This is not just normal cosine, it's hyperbolic cosine. So the value is here, mean stress, which is a scalar, and sigma ys is also a scalar. This guy is the yield strength of the material, and the 1 minus 1 plus F0. So if this equation holds, that means the void is going to crack, going to propagate. Okay? You understand, guys? And how to see if this one satisfies this equation is satisfied or not? If we have loading condition, you can calculate divitoric stress, and then you plug in. You have for this material, and you have yield strength, and you can just plug in to see if the left hand equals 0 or not. If it equals 0, that means what?
Oh, there's just like a bug. No.
The fly or bug?
Bug, like a bug that can fly.
Okay. Okay.
Something.
Okay, something. Okay. Some any questions? Any questions, guys? Question. So this model analyzes the plastic flow in a porous medium. Because we have F here, F is a current void fraction. If F equals 0, it means what? If F equals 0, that means a continuum. This is not a porous material. Now, by the way, guys, now currently, the porous material is very famous. Now say famous. It is a hot research topic. Why? Because it is light, right? Lightweight, and also as long as the strength is good enough, people tend to use the porous material. That material behave as the continuum. So porous material behave like a continuum. And then we talk about the Thomson. Thomson is another genius. And Thomson proposed a simple limited load model for internal netting between microvoids. So now this is, we suppose we have multiple voids here. So this model states that a failure occurs when the net section, this is net section, okay? Suppose we have the two neighboring the voids, and between these two neighboring voids, that is called the net section. When the net section stress between the voids reaches a critical value of sigma nc, n is net, c is critical. N here is net. Net means the area between the two voids. You understand? Look at this equation. Sigma 1 and the sigma 1 is here, okay? So this sigma 1 is the remote loading. Can I write down this? I did not write down here. So suppose this is a sigma 1, this is sigma 1. I have the remote loading. And D is the width between the two voids. D plus B, right? D plus B. So D plus B divided by D. If this one is less than the critical stress value as the net, okay, no crack. However, if this equation is satisfied, that means the fracture might be propagate. Okay? It's zero, it's equal means that's very, very critical state. You should know that, okay? So here, this width, horizontal width makes sense. This is vertical width does not make too much sense in this case model. Okay. So the Thomason the model is of limiting practical value and avoid the interactions and leading to a double fracture are far too complex and to be captured by a simple area reduction model. Now I just tell you this is a model, but it is not commonly used one. Questions so far? There are several models. Trust me, guys, I will not ask you guys to use the models to do things, right? But you should know that. Bobby.
Are these like a lot of the earlier initial models?
Yeah.
Okay,
Yeah, really initial model.
and then like they get more accurate as time progresses and
Yeah.
things like that, okay.
Yeah, the time progress, because especially because the numerical methods, the development of numerical methods. And we can use abacus or answers to do these things very, very accurately now. Okay? But as I said, we should never ever read other people's comment on other people's work many years ago, right? Otherwise, that is unfair. Right? For example, Newton's the three laws. For us, the three laws are very simple. But 300 years ago, in the 1970s, 16 something, that Newton's three laws, that is genius. That's a groundbreaking discovery, right? But even now, this if you have finished middle school, you know three laws. But 300 years ago, we should not. Definitely, Newton, Isaac Newton is always the number one person I admire, at least from my perspective. Okay. Yeah, as the time goes, people have developed more and more accurate models for prediction. Questions so far? No questions? So now this is for the fracture and for the ductile material. And then we talk about for this is cleavage. As I told you guys, cleavage is a very, very special one. The cleavage mainly is for the brittle material. As the name suggests, cleavage means if there's a crack and the crack will propagate until so this crack goes through the thickness section of all this this is a cracked body, and then this can totally fill. Right? So this cleavage should be prevented by all means. The rapid propagation of crack along a particular crystallographic the plane. And whenever you see this word, I think if you have taken material science class, so this something come into your mind, right? Crystallography. Right, guys? Okay. So cleavage may be brittle, but it can be preceded by large-scale plastic deformation flow and ductile crack growth. The preferred cleavage planes are those with the lowest packing density, and since fewer bonds must be broken and the spacing between planes is great. Right? You guys remember something in the material science? So microscopically, when we say the material breaks, what comes into your mind, guys? Can someone tell me? I say, so this is, for example, this a piece of paper. It is a break. It's a broken. What does it mean? Can somebody tell me what is broken? Okay.
The bonds fracturing. Like the
Yeah.
bonds break.
Yeah, that means before I break this material, right? So I know along this line, there's atoms, they are connected by bond, right? Breaking means that by some means, I just break the bonds that these neighboring atoms, they are separated. So this is the physical meaning of fracture or breaking. So when we do some materials, especially for these metallic materials, it's the same thing. We apply some load, and this load is so huge that some bonds between the neighboring atoms, and they are broken. And then there's a microvoids, and these microvoids coalesce together and then have a bigger crack. So for cleavage, if we break, it will break until the workpiece is filled. So the nominal orientation of the cleavage crack is perpendicular to the maximum principal stress. You guys agree? You can maximum principal stress means what? Maximum principal stress, that is tensile stress, right? It's a tensile stress. The maximum tensile stress can have much more obvious effect for the breakage between the atoms. You guys agree? So always when you apply some stress, after you do the stress transformation, you will find the maximum tensile stress value, right? Maximum tensile stress value, and when in the orientation that is perpendicular to this tensile stress value, maximum tensile stress value, it tends to break. It has the most tendency to be broken. So BCC, you still remember BCC, FCC, and HCP, guys?
Body center.
Huh? Say again?
Body center.
Yeah, BCC is a body center the cubic material. And FCC is a face centered cubic material. And HCP is hexagonal close packed material. So this is HCP metals are susceptible to cleavage fracture. So do you have the textbook, guys?
Online, yeah.
Okay, if you have a textbook, you can look at the corresponding figures And to save space, I did not give too many figures here. I'm sorry, guys. But I will, if you have, this is the textbook, either hard copy or on this online, and this is the ebook, and you can look at the figure, okay? And so this is the three, and the BCC, for example, BCC, in the case of BCC, cleavage occurs on this 100 plane, the fracture, the path is transgranular, in the polycrystalline metals, for this one, a cleavage plane, and those with lowest packing density. Cleavage plane. Why it goes to along with the lowest packing density base? Why? And you can imagine, along this line, and we can use minimum energy to break it. Okay? You understand that? So the density, 100, this is, we have x, y, z, okay? 100 means in the x direction. The density here, 110 means the x, y, the 45 degree, but it's in the x, y plane. This is, you can calculate how many atoms you can have. So these, they are lowest packing density. They are very packing density means within the certain length, how many atoms you have. That is called the lower packing density. So the propagating crack changes direction, and each time it crosses a grain boundary. And the crack seeks the most favorable oriented cleavage plane in each grain. Do you guys agree with that? Do you guys agree? Yeah, using the minimum energy potential, using the principle of minimum potential energy. Right? They always seek the path that requires the minimum energy to break. So this is FCC, and I'm going to talk about this one. We have 1 minute. I'm going to stop here, guys. And FCC is copper, aluminum, and this HCP, and for example, then. So I'm going to, as I said, I hope you guys take a look at the figures in the textbook. So this is today's class session, and if there's any further ado, I'm going to end.